I just started the video capture again, and I wanted to say that there was one class that was missing. I don't know how I managed to overlook that. It should be up as soon as I can get it up, but all the other classes have been put on Blackboard with YouTube. So you should be able to see all the previous classes, and you got videos of them if you could go back and look at stuff if you're not clear about things that I said during class. Sometimes I'm not clear about the things I said during class, and now we have a record of them all. Some other announcements are that the fourth problem set is due on this Sunday. It's the last problem set before the midterm, and next Tuesday, the next time we meet here, will be an in-class review session for the midterm. I wish I'd written it on the slide. Please bring questions for me for the review session. That would really be helpful. I will go through the spring 2011 midterm exam, so you don't have to bring questions, but it's always better for all concerned if you bring questions. Thursday, then, next week, a week from today, will be the midterm exam, and I'll say more about that in a second. For 5 additional points of extra credit, again, you can turn in the spring 2011 midterm exam by next Tuesday. So there is a deadline on that. Just print it out, fill it out as though you're taking it. You've got the answer key available, and you'll get 5 points extra credit in the midterm. So here's the slide on the midterm exam. The coverage I talked about before, it covers chapters 1 through 6 with greater emphasis on chapter 5. That's the solo model. And if there were one thing that you can study, that should be it. If you don't study anything else, you should study the solo model in chapter 5. Chapter 4 is also important. It's got the marginal productive labor curve that slopes downward in labor supply and what happens when labor supply changes and that sort of thing. Chapter 6 is the Romer model that we'll finish up today, and that is important. You'll probably see something on the exam with that, but it's less important, I would say, than the other stuff. It'll look similar to previous year's exams, but it'll be entirely different questions. So now we are at this decision point. Frankly, I did hear about this climatic change in the room before today, but I didn't believe it. And I'm sure you wouldn't have either if you had heard about it. To me, this is an acceptable state of the room to take an exam in. Let's play it by ear. We have next Tuesday to see beforehand. If the air conditioning conks out again next week, then maybe we'll make a change. But I guess if the room is like this, I think we are better off taking the midterm exam in class, and here's why. If I give you a take-home exam, I've made these promises here at the bottom 2 bullets that I will deter academic dishonesty, but it's a lot harder for me to do that on a take-home exam. Now, I would be the first to point out that the vast majority of you in the class here, and probably everybody who is here currently in the room with me, has no intention of cheating and never does. But there are some very small numbers of students who do cheat, and it's a real pain in the butt. And so that's my promise to you, all the good students who are here, that I will deter academic dishonesty. The problem is that it's harder to do that on a take-home exam, and I haven't really figured out how to do that yet, but I could if the climate deteriorates again. But my feeling is if it's like this, then we should go ahead and have an in-class midterm, because you will have an in-class final exam. It'll be in December, and I think by then, for sure, it won't be hot in the room. So this is still a little bit yet to be determined. I will keep you updated. You're welcome to send me your thoughts about this over email. A student did earlier yesterday, and that's more than welcome. Please do tell me your thoughts about that. My biggest concern is that if I give you a take-home, I think you would agree with me that it's not entirely clear that your effort is going to be rewarded if others might find a way to get a leg up on you with collaboration or other sorts of things. It's kind of a tough thing to do. If it were essays, I mean, that would be one thing, right? That's easier to grade, and because it's easier to make sure that nobody's copying them. But probably half of the class would say, I don't like essay exams because I'm uncomfortable with that. I'd rather have multiple choice. And, so it's kind of this wormhole that we go into. So if you're welcome to tell me your thoughts about that, but that's my current thinking. Sorry? I'm sorry? We could take a vote. Yes, we could. I'm not going to ask for a vote, though, on this. You are welcome to express your opinions to me over email or in person, as you like. A student asked about tutoring, and I apologize for not being more on top of this. This was in my inbox back in September, and I just completely missed it, and I'm sorry about that. These are the times for course-specific tutoring for the economics courses. For us, econ 201 and 202 is here in the second row, and some of the Thursday time is unfortunately overlapping with this course, but much of it isn't. You could go to tutoring right after you're done here, in fact, if you wanted to. So there's what you want to look at for this course's tutoring. The other courses also have tutoring if you're interested. And once again, I apologize for not noticing this earlier. I honestly didn't see this, and the problem is with an email inbox that's full of other stuff, it just escaped my attention, so I'm sorry about that. Any questions about tutoring or the midterm or problem sets? Okay, well, let's move on. And much of this class today will kind of be review of stuff that we covered on Tuesday, but I think that's helpful. Why are we studying the Romer model? Well, it's because the Solow model is not a complete story of reality. It cannot and does not explain long-run growth. In other words, capital accumulation, which is the story in the Solow model, and is a very realistic story and an important part of reality, it does not, in and of itself, explain long-run growth. And that is probably very easy to accept now in 2013. Back in the 1950s, it didn't necessarily seem that that would be the case. That in the 1950s, economies were very centered around building capital goods and industrial products. It was a different economy back then. And in fact, one of the beliefs was that economic growth in the long run could be achieved with higher rates of saving and capital accumulation. It can, in the short run, create some economic growth, but the main and very valuable insight that we have seen now is capital accumulation alone will not give you long-run growth. It cannot produce sustained increases in well-being over long periods of time. That's probably part of the reason why the United States has evolved toward an economy that produces ideas rather than just capital goods. We still produce capital goods as well, but there's a reason why a lot of the capital goods that we purchase are actually built elsewhere, say in China. Practically, what does this mean? Well, suppose you have high rates of saving, like where? Well, like places like China, but also other countries along the Pacific Rim, like South Korea and Singapore, I think is another example. We'll see this at the end of the slides today. These are countries that have very high rates, of saving. Well, suppose you have that. Is economic growth rapid in the short run? Yes, provided that what has happened is an increase in the rate of saving to a high enough level so that there is transition toward a much higher steady state. But in the long run, provided that there isn't a continuous increase in the saving rate, that's going to eventually die away. At least not without something else and the something else is going to be technology. So, did I talk about this earlier, the movie Pacific Rim? Everybody who's got like a 10-year-old boy inside them should go see that movie. It was out on DVD this last week. It's good stuff. It's big robots. Awesome. Okay, so the Romer model is a two-sector good that is all about explaining where ideas come from and what the constraints are for economies in producing ideas. What sorts of things do economies need to give up in order to produce ideas? This has a clear parallel to the Solow model, where what is it that economies have to give up in order to get capital? Well, how do they get capital? Well, they save. So what are economies giving up in order to get capital? Consumption. They're giving up consumption, spending on stuff that's fun. And not to be stereotypical about this, but there's a connection here that in China and other Eastern economies, the mindset of many consumers is one toward delaying consumption, saving for the future, and not consuming now, but consuming more in the future. So there's a real cost to saving, and it's that you don't get to consume as much today, and that is kind of a real bummer. The other thing to say in this regard actually is that in some economies, most notably it's China, consumers don't have opportunities to spend on consumption as much. The markets are not as developed, the infrastructure is not as developed as it is here in the United States, so goods cannot get sent all over the place and we can't buy them as easily that if we were to be living in China, for example. But it also has to do, quite honestly, with tastes and individuals' perspectives toward consumption today versus consumption in the future. It could have to do with households in which individuals are raised and their past experiences. Much has been written about how children who were born into U.S. households during the Great Depression were very frugal with their spending. They would not spend as much today, save more, and wait to make sure that they could survive in order to get into future periods. And why? Well, they were born into households during the Great Depression where, in fact, things were pretty rough. Okay, so that was a very long-winded detour, but the point is that in the Romer model, there is also a cost to producing the important input here, the ideas, and that is that the labor that is used in producing ideas, the scientists, cannot also be used to produce other goods, farm production, basically. The scientists are not also farmers. So I'm really, really sorry. I was in bed all day yesterday, and I'm a lot better today, but my voice, as you can tell, is not quite where it should be. Okay. Here's the goods production sector, where the amount of food is uppercase Y, that's the output in the economy of goods, and it's what people need to eat, is equal to the number of ideas, that's the technology stock, uppercase A, times the labor in goods production, that's the number of farmers, L sub Y, and here I've left off the T subscripts that tell you that things change over time. Well, that in turn then we assume is equal to uppercase A times this, if you like, the farmer share, 1 minus L of the total population, N. So here, L is actually a lot like the saving rate. It's the amount of the resource that you have, people, who are saved out of, say, farming and put into laboratories so they can come up with ways of figuring out better production methods. So they show up here in the second line. Excuse me. The new ideas produced are equal to a productivity parameter, little z, times the stock of ideas already existing, uppercase A, times L sub A, which is equal to script L times N here at the last part. It's the scientist's share, the share of the labor that is saved and removed from the fields and put into laboratories that then ends up helping produce ideas. Okay, so the magic, how do you solve this model? Well, it really, like I have said, it's about solving for the endogenous intermediate input that's produced. It's in this case here, it's solving for uppercase A, the stock of ideas. In the solo model, it's solving for uppercase K, the capital stock. So that's the same in both cases. You're solving for the produced factor that's important there. But the way we're going to start is maybe a little different. Well, we could just begin that way, I guess, first, but the way the textbook does it, the way I've done it here in the slides, is start by thinking about output per person, which means farming output or food produced per person. So what we've got then is uppercase Y is equal to A times 1 minus L bar times N. Dividing both sides by uppercase N means that it falls off of the right-hand side. And what we've got left is uppercase A times 1 minus L bar. So eventually what we're going to do is plug in a formula for this. That's kind of the crux of everything. We need to have a formula for the stock of ideas at a particular point in time. That's the most valuable part of all this, and that's why I kept hammering on this point that in the Romer model you've got to solve for the endogenous produced input, which is its ideas. In the Solo model you solve for k. That's always the way forward. Okay, now I've put in the subscript t here on ideas. Well, what's the level of ideas that isn't constant? It turns out that it grows exponentially, and to see why that's true, take the idea production function and divide both sides by uppercase A. How do I know how to do that? I think that's a question that should be in your minds, and that's one I get every term. Well, I'm taking what I know, which is this line, and trying to figure out something about what I need to know using it. And it turns out that delta A over A, the change in A over A, is the growth rate of A. So it's a little bit of algebraic magic and pattern recognition. Typically, on an exam, I would give you a hint about what to do here to try to solve for, say, I would maybe write this down for you, that delta A is equal to Z times A times L bar times N. And I would say, well, use this and solve for try to find an expression for the growth rate of A. And then you would be on the hook for remembering that the growth rate of A is actually the change in A divided by its level. I admit, though, it's a little bit confusing. Well, if this happens to be true, and if these parameters are constant, by assumption they are, now, of course, one of the big problems here is that the level of population actually in the real world is not at all constant. And at the PhD level, these models tend to take more complicated forms because they account for that. That the fact is that population actually grows over time. Leaving that aside for a second, if this is the case, so there's a growth rate of A and it's equal to Z times L times N, well then we know that it must be true that the level of A, then, if it grows at this rate, has got to be equal to this math, where A0 is the starting level, and 1 plus this growth rate here, ZLN, 1 plus the growth rate to the tth power is the next part that multiplies all this. So that's the heavy lifting here. Is everybody okay with this, or do you have questions about why this is true? This is awesome. I love how I can actually hear everything in the room right now. So this is a great time to ask questions because I can actually hear you. Yes?
How does the last formula connect to the top one?
The question was, how does the last formula connect to the top one? It doesn't yet. That's a good question. The very top formula is the other side of everything, if you will. Let's just back up for a second. So just try to remember the top formula is the formula for Y over N, or output per person, and it has an A in it and a 1 minus L in it. And the bottom formula is a formula about ideas. Backing up for a second, sorry, how far do I want to back up? I guess one more, I'm sorry. There we go. It's coming, those two things are coming from two different parts here. The top formula is coming from the top formula here that is telling us about production in the farming sector. The bottom formula is coming from the bottom formula here, it turns out. So there are two different production functions. And so on the next slide, where we've arrived at here, here's the bottom of this slide. We started with this top equation, and that's what it implies. Excuse me. And then here I've written it up at the top. On the previous slide, the second production function is what I've reproduced here, and that implies this guy. So they're not yet associated with each other at all. That's the next step, actually. If these are both true, the guy at the top and the guy at the bottom, then we can substitute, using the bottom one, substitute into the top one. And so combined then, I should have color-coded these or something. What we're doing is taking this guy and combining it with the top one. So here's an A, here's an A, and we're going to substitute this guy in up here. And what we get is output per person, so in words, output per person equals the initial stock of ideas times 1 plus the growth rate of ideas to the tth power times 1 minus the scientist share, L bar. Yeah.
The T power,
Yeah.
you can put any years.
Yes. Okay, so the question is, what's up with the t that's in the power there? What does that mean? And the answer is it means years. You know, that index is time or years. And so what it's telling you, in fact, I wish I had put it here. There should be a little subscript right here, a little t. So what it would tell you is that y in 2014, let's say, is equal to A0, which means productivity, number of ideas in year 0 AD, times 1 plus the growth rate to the 2014th power, times this. It would tell you the level of income per person, you know, starting, if this were true, if we had constant population all the way back to year 0, and a constant scientist share all the way back to year 0. Now, we didn't, right? That's the problem. But that's what it's formally telling you. And it also is true for any other level of t. You could think about generalizing it to different starting points, not just year 0. It doesn't actually have to be 0 AD. It could be, year 0 could be redefined as the year 2000, if you like. Other questions? I'm really sorry. I've had this horrible cough and it's been really bad. But I'm getting better. I'm getting better. What have we found? This is exponential growth in ideas and also in income per person. And that may sound a little strange. We've often found, well, you would in, say, econ201, that actually capital would be growing exponentially. And then the question is, well, what's happening to income per person? And it turns out that it isn't growing exponentially. And the reason in that case is that capital is a rival good. You can't use it all over the place all at the same time. In the case of ideas, that's not true. Ideas raise income per person for everybody, which is really rather magical. It's because ideas get to be used in idea production. These are the scientists, remember in the example we asked last class, and in farming production all at the same time. Exponential growth, when it's on a ratio scale, looks like a straight line with slope ZLN. And this is kind of cool. So far in the class, we haven't seen a model that actually does this. In the solo model, we just end up getting a steady state over long periods of time that is just flat. So why is there growth? Ideas are the engine of growth here, and it was capital in the solo model, and we saw this last time. The idea accumulation equation shows constant returns to ideas and idea production, which is rather remarkable. The exponent here on the level of ideas is equal to 1, and that's very different from this story. In the solo model, inside this production function, the exponent on capital is only 1/3. So there are these decreasing returns to capital in capital production because of the diminishing returns in capital to the production function. Why is this true? Well, again, it's the story that, that ideas can be used all over the place all the time. Capital can only be used by a given amount of labor. Now, as I discussed last time, there are some issues with how you apply the Romer model. What parts of reality does it explain? What parts does it not explain? One of the central results is that the growth rate in income per capita is the same as the growth rate in ideas, which is a linear function of the population size. Here, so the growth rate then of output per person is equal to the growth rate of ideas, G bar, and it's equal to Z, the productivity of scientists, times the scientist share, L bar, times the share of the total population. And so based on this, you would expect to see that larger countries, other things equal, would have faster growth The reason is just here, that if a country has a larger N, it would have a faster rate of growth. And the deeper intuition as to why it would is it's technically because there are more scientists. So if two countries have the same scientist share and one is bigger, that means that one has also more scientists in addition. And generally, around the world today, it's not really necessarily the case that bigger countries have faster rates of growth. So one example here is that Luxembourg probably has fewer people than US scientists. So there's no way it could possibly have more scientists than the United States. Yet it's had a faster rate of growth. And so in the modern economy, the problem with thinking in the mode of the Romer model is the following. Ideas that get produced in particular countries may not be limited to just that country's borders. Ideas are very non-rival. You can use them all over the place, all at the same time. And we're not talking about necessarily corporate espionage, but it could be. But once production techniques have been used for a while, this is kind of the Samsung and Apple story, right? So that Apple produces the iPhone, Samsung sort of figures out everything that's going on with the iPhone and duplicates it, and then they go to court and they fight each other and all that, and that kind of keeps going back and forth. Samsung, I think, I think it's wholly owned by, I think it's South Korea, right? I think it's a South Korean company. Apple is a North American company that it gets its hardware out of production in China, but the profits all end up back in the United States. So I guess you could look at the struggle between Samsung and Apple as this struggle over the ownership of the ideas of like it's the pinch to zoom thing, on a smartphone. Is that an idea that somebody can own? Or is it just an idea that, no, come on, that's not something you can patent and own all that. That was kind of one of the problems here. So basically it's gone this route that coming up with that idea, there was no way to kind of keep it. And that meant that you might see faster growth in the country that's producing, say, the Samsung stuff. Okay, I apologize. I'm filling the air with coffee. So the Romer model really is best for describing world growth over long periods of time. And here's this remarkable picture showing that world population in millions in the blue line here actually rose before income per person rose. It rose first, indicating that there was an increasing level of the population, which then, in the Romer model, feeds into a faster rate of growth in ideas and in person GDP, which is what's plotted here. Now, why is this so remarkable? Well, why would world population rise? You need income to live, right? I mean, it's kind of cool that this is actually happening here in a way that's sort of predicted by the Romer model. You might expect, if anything, it would be the reverse relationship. If you thought about how income is kind of necessary not to die, right? So you might expect income to have had to have risen first, and then population would follow. In fact, it looks like it was the reverse. And one of the deep questions in science in general, I guess, but human sciences, social sciences, is exactly why this happened in this way. One of the possible explanations is the Romer model. That, you have, for whatever reason it was, you have more people, and that produces this endogenous growth. So what else affects growth? Well, there are 4 different parameters aside from the size of there are 3 aside from the size of the population that affects the growth rate. So we've talked about the size of the population, but then other things that are important here are the share of the population in science or ideas. And that's kind of like the saving rate from the Solo model, but obviously a bit different. Also, the productivity of scientists and the starting level of ideas. These are all parameters that change stuff in the model. And so what you're on the hook for is being able to think about how changes in these things change the picture of growth. You know, what do they do? Do they change the growth rate? Do they change the level of GDP per person? Or do they change both? Or neither? I wouldn't have written them up here if they didn't do either one, but it turns out that there are some interesting differences between how these things affect stuff. So technically there's no slow transition in the Romer model, only a balanced growth path that you kind of immediately jump up and down to. And so the picture maybe will look a little strange. Let's just think about this. Suppose we were to imagine an increase in the population. And here for a country, it could be new immigrants arrive, and so they swell the population. For the world at large, it could be, well, suppose the global climate becomes a little bit more hospitable, and so crops don't die off as much, and so people are able to survive more, so the population rises. So when N increases, what happens to growth in income per person? The other part of the question is what happens to the level of income per person, little y? Well, prior to the change, when the population is its original level, n bar, there's some constant growth at g bar. So now what happens when n rises? So again, the two questions here are level of income per person and the growth rate of income per person. I think you will find this is exceptionally confusing, because what I've shown you here is a formula for the level of yt, and it looks like n is in the level of yt, right? You know, here it is. But the thing is that is the growth rate component, this bit right here. So when n changes, it has a very small, if any, effect on the level of income per person. It just changes the growth rate. So the story is going to be stuff in this part, ZLN, affects the growth rate of income per person. With an increase in population, you might think about this in your heads, well, you know, what determines the level of production per person? Well, it's basically the number of farmers per person and the ideas that exist. Well, if I increase the number of people around, the number of people increases, obviously, but how fast does the number of farmers increase? Does it increase at the same rate as population, or a slower rate, or do you need more information? Yeah.
It would increase at a slower rate because the portion of those people that are in the population are attributed to science or ideas.
Okay, you're on the right track for sure. So the suggested answer was the number of farmers increases at a slower rate because you need to have scientists. I'm paraphrasing. The thing is that the number of scientists is equal to a constant share of the total population. And the number of farmers is equal to a constant share of the total population. So in your head, what you should be thinking of is if there's a growth rate in N, what's the growth rate in the number of farmers? Well, the number of farmers is 1 minus L times N. Now take the growth rate of that. You get the growth rate of 1 minus L plus the growth rate of N. Well, what's the growth rate of 1 minus L? It's 0. Yeah. So provided that the farmer share, or equivalently the scientist share, stays exactly the same, it means that an increase in N, or a decrease in N, will do absolutely nothing to the number of farmers per person, which is important for income per person. So that's the intuition for why this looks the way it does. Excuse me. There's no jump, and it's because the number of farmers per person doesn't change, because the number of, the share, I should say, of scientists, or the share of farmers in the population stays exactly the same. So there's an increase in the growth rate, but there's no jump back here. Production per person is what it is. Suddenly, with more people around, however, there's faster growth in ideas, and that's what fuels this takeoff here. Okay, were there other questions? Okay. Is this realistic? Over the last century or so, not really. Over long historical periods with steady population and originally no growth, it is, yeah. Okay, now a bit of a different question now happens, and I alluded to it in this discussion that we just had, when we think about the following. Suppose there's an increase in the scientist share L bar. What happens to income per person? Now, you could look at this a couple of ways to develop intuition. Remember that I said this parameter, the scientist share, is a lot like the saving rate in the Solo model. If you increase the saving rate in the Solo model, what happens to income per person? It increases. What I guess the unfortunate fact is going to be that, so does it increase immediately? Does it jump up in the Solo model? And the answer is actually no. It just starts growing really, really rapidly. And that's going to be a little different than this story, but still the intuition is similar. How about what we just talked about on the previous slide? Suppose instead of increasing the population, you're increasing the scientist share. Does that change the farmers per person that are out there? And the answer is yes. And that's important for income per person then. So the confusing thing here is that we start off, originally we're at this situation where there's a steady growth rate. Now, if this thing were to rise, well, it increases the growth rate. And, again, I think we are programmed to see, well, the derivative of y with respect to L, it looks like it's kind of positive because of this thing. But I guess, it's hard to get beyond that. It's hard to remember that this is the growth rate component. It's going to be a number that is not very large. This thing is about 0.02 or something, 2% growth. And I admit that that's totally impossible to see here, but the point is that that's a growth rate effect. Here, however, is going to be the level effect. And when L increases, what happens to the level of Y if this is the level effect piece? L increases, and then what happens to Y? It actually goes down. So you had a question. Okay, so I should keep, okay. When L increases, Y goes down. It's because L shows up over here. The growth rate of Y gets larger, but the level of Y actually goes down. So there's this story that the growth rate increases. What's happening, there's reallocation of labor toward ideas, and it removes labor from goods production. It takes farmers out of the fields and puts them, put them in a little white lab coat with little Poindexter eyeglasses and all that stuff, right? And so they become scientists. And what that means is that they are no longer producing farming goods. And that's bad for farm production. So a way of looking at it is that YT is equal to whatever the stock of ideas was times 1 minus L bar. That's something that we had kind of derived a bit earlier. So if L bar rises, what happens to YT? Well, this doesn't change in the short run. It's growing. But if this rises, that means that this whole thing has to fall. And so that's the story here. That there's actually an initial drop, a jump straight down in the level of income per person. Questions?
Once it drops with the slope, the higher slope, a bigger slope?
Yeah, the slope is steeper there once the drop has occurred. And that means that there's faster growth. So the slope is equal to this new G bar prime. And that's this larger number when L prime, is increased. So the product is higher too. This might be a little hard to do with the graphs already up here. So we've talked about N changing, that's the population size. We talked about L bar changing, that's the share of the population in idea production. That's what this slide has done. What are the other things that can easily change here? Well, there's A0, the beginning stock of ideas. So what would happen if the economy began with a higher, initial stock of ideas? If none of this were going on, and if A bar 0 were to be higher, what would you see in this graph? Would it change the growth rate and the slope? If A bar 0 were larger and nothing else were changing, it would not change the slope and the growth rate because A bar 0 is not in this piece, which is the growth rate. The growth is determined by basically the number of scientists that you've got. They use the ideas that are around, but that doesn't determine the growth rate. It's the level of the ideas and the income per person. So it would be a level shift. If A bar 0 were higher, the whole thing would just be shifted up. If it were lower, it would be shifted down by an equal amount. So it's a level change. It's better to have more ideas. Another way of thinking about it would be, suppose, this is more outside the box here, and maybe, I wonder if I should just back up to the picture here so that you're not confused by what I've just said. Okay. What if there were a one-time, say, library fire? How do you store ideas? Well, people remember them, but you also might have to write them down. And of course, this was a huge issue, these libraries and what happened to ideas following the fall of the Roman Empire and human history. During the Middle Ages, did the ideas actually get saved, or did it all just get destroyed? And it was a kind of a horrible time where there had been, civilization and ideas and society and production and all that, and all of a sudden it all crumbled, and we went into the Dark Ages, or the Middle Ages, you could call them. Can you think of a way to model the Dark Ages here? So, suppose what the Dark Ages consisted of was a one-time destruction of a certain amount of the ideas that are out there, a certain library fire. Right? The fire burns like half the library, so it burns half the ideas that we have. Nobody remembers what they were. What would happen here? Would it change the growth rate? It wouldn't change the growth rate as long as what I've said is the whole story. What affects the growth rate? It's the productivity of scientists, the scientists' share, and the population. What I've said so far is none of those, doesn't have anything to do with any of those. If, say, half the ideas are destroyed, what you would see is a reduction in this, I think, by a factor of 2. It would just jump straight down, and then what would happen? It would just grow the same level after at the same rate. Excuse me. So a downward jump, a bunch of ideas are destroyed, and then a resumption with the same slope after that. Okay, this is a tough model, right? I'm not sure we got that, and the problem is I haven't prepared a slide actually saying that clearly, so I apologize if that wasn't clear. These are things we can talk about in the review session next Tuesday. Let me go ahead and move ahead because my voice is really failing me. I'm sorry about that. Where to next? Let me just say a few more things. I'm sorry, I backed up accidentally. Let me just say a few more things about what we have seen and what it means. Before I do that, I should ask, are there any questions about the Romer model? And feel free to ask them today or next Tuesday. Okay. Tough model, not easy. Yeah?
Does the Roman model and the Solar model, they increase at the same rate?
The question is, in the Romer model and in the Solar model, do the economies increase at the same growth rate? And that's a really good question. And the answer is no. In the Romer model, what happens to growth in the long run? I'm sorry, did I say Romer? Let me start over. In the Solar model, what happens to growth in the long run? It's zero. And that's kind of shocking that even with saving It runs into diminishing returns, and ultimately the growth in output and output per person is zero in the long run. In the Romer model, what's growth in the long run? It's Z times L times N. It's the productivity of scientists. Scientists have to be productive. I mean, that's one of the problems, right? If your scientists are all lazy and they don't do anything, that'd be a problem. Alternatively, you have to have some scientists who are productive. That's the L bar term. And you have to have a population, but you actually get long-run growth that's positive. And that matches reality. So in fact, there are very different stories that pop out of the Solow and Romer models. Other questions? Yeah.
So would reality actually combine these two models into constant growth with relation to saving?
Yeah, the question is, would reality combine the two models together, the Solow and the Romer model, with steady growth and a constant saving rate? And the answer is absolutely, that's right. You can look in the textbook. It's in the appendix. I think when I first started teaching the course, I actually showed students the model, and it didn't go anywhere. It's a very difficult model. It's really not something that I thought was very productive to spend class time with, but it's there. The thing is, one of the deeper questions, I think, is unresolved, and that is the following. In the Solow and in the Romer model, we have these saving rates, so to speak. We have the saving rate out of income, and that needs to not go to 100% because you've got to consume something, and that's reasonable. In the Romer model, you've got this share of the labor force devoted to science production. One of the deep questions in macro is whether these rates of sort of saving, if you will, or accumulating factors, and not just having a fun time right now, but planning for the future, these rates of saving. You could think about another rate of saving that we didn't really formally approach, but the rate of saving that is represented by the amount of your life you spend in school. That's saving, right? That's time that you are spending investing in yourself. And if you were to think about the time in your life spent in school as a share of your lifetime, that's a certain saving rate. And you might then ask, are we finding that we need to spend more and more of our time in school? Save more, basically. And the jury actually is a little out on this, whether, in fact, we are going to see sustained growth in reality with steady rates of saving, or are we actually going to need to keep accumulating factors more and more and more to actually get growth that isn't zero? So that was the long-winded answer to the question as it really matters in reality. Kind of an interesting one, and I think we don't really know. Other questions? All right, well, let me just say a few more things. What we've seen is that the Solow model does some things really well, and key among them is why countries grow at different rates for decades at a time, and it's based on how far away they are from their steady states. Countries that have increased their saving a lot, like China and South Korea and other places as well, I think Ireland might be one of them actually, are transitioning toward these higher steady states, and that's why they have faster rates of growth for decades, faster than, say, the United States. They're still at a lower level of income per person, but they have faster rates of growth. And so the examples that it fits well are post-war Germany and Japan, also Korea and other Asian tigers. And we have now seen how the Romer model can explain the critical element left unexplained, the source of long-run growth. And these two can be combined. I guess I do have a picture of this, but it's not going to be on the exams. If these are, get combined in the appendix, you can see a graph that looks kind of like this. There's long-run growth in income per person that derives from growth in ideas. Suppose along this growth path, then, there's some increase in the saving rate. So that gets you the transition dynamics toward a higher balanced growth path. And it would look kind of like this. So if the country sees an increase in its saving rate, it would produce this higher balanced growth path, but only at the same rate of growth that's determined by, say, the scientist's share. So that, in reality, is what we see out there, this kind of thing. It's kind of an amalgamation of the stuff. And so it gets to your question. Takeaways that you should remember, well, not the math. Rather, the messages are, we have a theory of long-run growth that's driven by the discovery of ideas, and this is a worldwide kind of thing. And it's because ideas are non-rival and can yield increasing returns. We also have a theory about why there are differences in growth rates across countries, and it's about transition dynamics with changes in saving rates. Yeah, I guess that's really it. It's saving rates are the big story. I don't think I showed you guys this graph. And I showed the econ201 students a graph that looks at the saving rate by different countries in different levels of development, and it's just really shocking that very poor countries are not able to save very much, and the middle income countries save more, and the highest income countries save quite a bit. And that's really kind of a key thing. So we see different experiences, even though, you know, if ideas kind of flow freely across borders, you should probably see all countries growing at the same rate in the very long run. You don't see that, and part of the reason is their policies and choices, like their saving rates, are different. There are many other reasons, of course, other than, you know, scientists and idea production, why it might be the case that some countries have very low levels of productivity. One of them is the form of government, and there are many others. We've talked about that a few times. So it certainly isn't the case that the Romer model is you know, everything there is, the alpha omega of growth, but it fills in some very important gaps, and it's a useful thing. Let me now talk about what's called growth accounting. And this is another way of looking at the message that has already emerged, which is that capital can't explain big differences in output per person. It's really all about total factor productivity. And this represents ideas. It's also human capital, so we haven't traditionally measured education. And in fact, that does matter a lot. But it's also institutions. It's the rule of law. It's private property rights. And in fact, you know, it's total factor productivity that accounts for most of the differences in income per capita across countries or over space. And this sort of matches up with the story that we have seen, that over time, that's what the Romer and Solo growth models are about. A particular country over time, its ideas and total factor productivity are key for long-term growth in incomes over time. So let's think about the combination of these. So let's think about different countries and think about their growth rates over time and look at importance to growth in total factor productivity, capital, labor. You could also think about, and we'll do this, you could think about changes in, say, let's just call it the average work week. Do you have a sense for how that varies across countries? Like, what would you say is true about the length of our work week, like the number of hours worked per worker per week in this country compared to a country like France, let's say? Is ours higher or lower? Longer? Ours is, yeah, rather considerably longer, yeah, higher. And we will see there are some interesting things that pop out about this. It has been the case that hours were longer than in other countries than in the United States, but we still are maintaining a relatively long work week, and that you know, that's important. You want to know how many you need to know how many workers you've got, but you also need to know how intensively they are being used. That's important for growth accounting. So the math isn't important, but it does use the growth rate rules, and so that's why I left it in here. What we're going to do is just take growth rates of both sides of this to start, and then a little bit of extra algebra to kind of break it into components that we are going to measure. So here, I'm not sure why I did LY, but I guess, you know, the point is that it's the people involved in actually producing GDP. One of the interesting things, and you can't actually research this right now because the government is shut down, but there was a change in the way that the government actually measures the value of idea production and, you know, the workers, you know, available to it recently, which is kind of an interesting topic. I guess it's best left for office hours. All right, so let's take growth rates of both sides. What you find is that the growth rate in uppercase Y is equal to the growth rate of A. And then what? Plus? Yep. Plus a third the growth rate of K, so that's kind of two steps in one there. Where I've got K to the 1/3, and so, you know, it would be plus the growth rate of K to the 1/3. Well, that's equal to 1/3 the growth rate of K. And then what? Plus 2/3 the growth rate of LY. Yeah. Okay, well now let's subtract, so I guess what we're doing is subtracting the growth rate of, yeah, I wonder what my notation means here. It's going to become clear in a second, but I think it's the growth rate of the number of workers as opposed to the growth rate of labor hours, I think is kind of what we're talking about. You'll see here in a second. So subtracting both sides, subtracting GLT off of both sides, what I've done, and it's because the data are arrayed this way, I've got 2/3 of the minus GLT here, and I've got 1/3 of it here. So what's going to happen is that there's a, this, you know, is the growth rate then of the ratio of capital per worker. And this is going to be the growth rate in the ratio, and I'm sorry I haven't made this clear, this is going to be total labor services per worker. And so what's important there is that we've opened up this way of measuring the work week. That's what this is. It's the growth rate in labor supplied per worker, and that could go up or down, depending on what happens to the work week. So the growth rate in income per person is the growth rate in total factor productivity, plus the growth rate in capital per person, I guess that's what I'm saying, and then there's growth in hours worked per person, and that makes, yeah, a lot of times when we measure this in data, you might think about it as per person, since that's what we ultimately care about. And the thing is that, you know, people or workers per person is you know, an interesting number. It's not one, and it's because some people are too young to work, some people are retired. And then the other thing to think about is, well, how many hours are the workers actually worked? And so hours worked per person combines these things. It's the participation rate in employment and then modified by the actual hours worked per employed person. So with this, we can decompose growth over time and income per person into the growth in these key components to better understand the sources. And there is going to be, excuse me, some action coming out of this guy, and certainly some coming out of this. So here's the solo model story, that there's growth in capital per person. But, you know, the thing about that is that if we measure it as being large, that's kind of a not welcome finding. We would like to see more coming out of this, and it's because this is what is likely to sustain long-term growth, if it's growth in total factor productivity. Well, let's look at these components over time in the United States. And how they've changed tells us some stories about the sources of growth. So we're going to divvy it up here into these different components. So that the very top row is income per person. Then we're going to look at growth in the components, or capital per person, hours worked per person, and in total factor productivity. And I think, you know, these are after the weights are in there, so they should all sum up to the top row. Well, looking over the entire, well, and this is now 10 years out of date, but, you know, the entire post-war period, income per person grew 2.5%, of which total factor productivity was a very large share. So 1.4 percentage points out of 2.5 is big. It's a little more than half. You also see capital per person. You also see increases in hours worked per person. And of course, I'm not sure if that's good or bad. I mean, hours worked per person, of course, means that not necessarily workers are working longer hours. It means that it could also mean that there are more workers per person, and that probably is sort of a good thing. I know if you're like me, you would not like to see your hours increase. I mean, I certainly wouldn't. The thing is that during this entire period, there were two very different phases of this, where up to 1973, here's the story with TFP growth, even more robust than in this period. And that's maybe a little surprising because of what we think of the economy back here. I mean, it was still kind of a heavy goods sort of thing, producing a lot of big, you know, industrial stuff. Following 1973, which was momentous for a variety of reasons, but it was the oil shocks and, you know, prior to the mainstreaming of computers in a lot of production, TFP growth slowed down rather considerably. But since 1995, picked up a bit, which is a good story. Now, here's the story for the United States. What have we seen? Well, especially in this later period, a fairly rigorous amount of capital per person contributing to growth. But still, a story that's fairly optimistic, I would say, about future growth, because a lot of it was coming from TFP growth. Now let's look at Singapore. Very rapid overall growth in the period 66 to 1990, where we get a 4.2% growth in income per person, but most of it, a very, very large share, was due to capital per person, and a very small share due to total factor productivity. So interestingly, there were these big differences in different eras. Here's there's 5 years in which there was rapid growth in TFP here, and then in another period where it really slowed down, and finally the last period in which it was, again, negative, which is not a good story at all. So rapid and robust growth in capital per person across the board here, but we would like to see this higher, and it hasn't been. So this is a story about the sustainability of growth. If it comes from growth in capital per person, like it does here, what do you think about how likely it is that the growth in Singapore will continue? Is it likely or not so likely? It's unlikely. Yeah. And it's because capital accumulation doesn't get you that far. It's the solo model. There are diminishing returns to capital, and ultimately growth is going to slow down and possibly even stop altogether. So this is controversial. It is what is implied by the solo model, but it's still, the whole thing is, as you can imagine, politically fraught and controversial. I should say controversial, shouldn't I? Controversial. Laboratories.
Hours worked per person.
Yeah.
Minus 1.1.
Yeah, I don't know what was happening there. I don't really know the full story behind these different numbers in these different eras here. And like I said, there are different things happening with hours worked per person. One of them is hours worked per worker. That could be going up or down or up or whatever. Here it looks like maybe down. But also you could get a negative number here if the workers per person were falling. And why would that be? Well, I guess maybe one argument that comes to mind, it's certainly possible that if you have tremendous growth in the capital stock, our view is that capital and labor kind of go together, they're complements. But they're also substitutes. And so it's certainly possible that their economy was substituting capital for workers back then. And maybe that's why workers per person was falling, and so it pulled things down. I don't honestly know. Any other questions? All right, well, what's been fun is to look at labor productivity. So, as I've mentioned before in the class, the problem with productivity is it's very hard to think of a way to measure it other than, as income per person. And I mean, that in and of itself is a function of, ideas and capital. So it's not really an index of ideas. It's the way we measure productivity. Here it is. This is the way everybody does it because it does make sense in this way. What's been happening? Well, a bunch of ups and downs. This is, let me think, what year is this? I should have put a year on this. This is a bit out of date now, of course. This was back, I guess, I probably put this in back around 2006 or 7. So there's more to the story here. But what was interesting is these differences in the trend growth rates that may or may not have persisted, and I think they probably didn't. But here, certainly, following the oil shocks in '73, a fairly lackluster performance with the trend in productivity growth up until maybe 1995 or something like that. Why would productivity growth have slowed, and then why would it have sort of picked up again? Well, what was happening during these periods, and why are the 90s so interesting? Well, it may be hard to remember, but the internet didn't exist before, sometime in the mid-90s. Even then, it didn't look anything like what we use it for now. Everybody who's looking at Facebook and Twitter can agree with me there, that those didn't exist very long ago, and definitely not, I mean, we're going on almost 2 decades now. So computers, I think, are a big part of this story, potentially, about the changes in trend. The other thing that this reveals is that there are these interesting fluctuations around trend, these ups and downs. And labor productivity is going to include effects of things like recessions. Here's a big one around in the 80s. Here's another one, kind of a drop-off here in the late 90s, and then a bit of an acceleration. And we don't yet have, isn't that interesting? There wasn't really any sign of the 2001 recession here. This is ending in 2003. So there are fluctuations around the trend in productivity if you measure it this way, and that's what we're headed toward in the second part of the class. So just to summarize, what have we learned about growth? Well, growth in ideas and growth in total factor productivity and not in physical inputs is really key to long-run growth. It's not as if you don't need growth in capital, but what we've seen is that that's not really going to save the day. The Solow model tells us about these short-run transition dynamics, and by short-run, I mean, we really mean several decades, which doesn't seem very short, I guess, but in the longer scheme of things, it is. It's a very different story if China, growing very rapidly right now, over the next several decades, continues to grow rapidly and then stops growing rapidly after, say, 30 years. That's a very different story than one in which China keeps growing rapidly for decades and decades and decades. And so you might want to know which one's going to happen, and it does kind of look as though it's going to be the former. That if the growth is fueled by capital accumulation, it's probably going to stop after some point. So the Solow concept of convergence towards the steady state is correct, and in reality we're really converging toward a balanced growth path where income per person is growing at a steady rate, And the things that matter for the balanced growth path, things like the saving and investment rate, they matter a lot for the level of income per person, if not necessarily for the long run rate of growth. So in terms of growth advice, or development advice, if countries can afford to raise their saving rates, they should, because it'll increase income per person. It's just that it won't necessarily produce sustainable growth. There are a lot of things that we've left out, though, that we know that other things are important for growth, like institutions, the rule of law, property rights, and education. There's a movement in the economics of growth, I think, to bring us all back to econ 101, which is all about property rights and Adam Smith and things like the division of labor, which requires that you trust other people actually, and markets and things like that. And I think there's a lot to that, for sure. So the next part of the class, then, concerns the wiggles. And that's probably what you thought you were getting into when you saw the topic of the course, as being macroeconomics. You probably thought about recessions and booms and all that. And these are called business cycles, and we're going to study them next. And we'll start by talking about employment and unemployment, and then inflation. And then finally, we'll talk about a short-run model in which fluctuations happen. Then we'll talk more in detail about government, and then trade and finance, international stuff, and all that. Okay, all set, lights on, 1, 2, 3, lights on.